Hi all, welcome to the 19th lecture on quantum mechanics. So in this particular lecture, I will be dealing with representation of momentum operator in position as well as in momentum basis. And in the second part of this lecture, I will be dealing with the representation of position operator in these two bases. Okay, so we know that the momentum operator acting on the momentum eigenvector gives the momentum eigenvalue times the momentum eigenvector. So here the ket P is the momentum eigenvector. So which is the eigenvector of momentum operator corresponding to eigenvalue momentum P. Okay. So then what we want is how will you represent this momentum operator in position basis? So the position basis can be represented as the set ket R. It's a continuous basis. Okay, so in order how to represent momentum in this position basis. So first of all, what we have to start with, we can start an inner product R P psi. So this inner product can also be written as R P times identity times psi. Okay, now this identity operator can be expanded in terms of the momentum basis using the completeness relation of momentum basis. So it can be written as integral dqp, the outer product pp times psi. Now this integration can be taken outside, integral dqp, and we'll have inner product r, the momentum operator p, then momentum vector p times p psi. Now what would be this inner product? That can be written as integral dqp. The momentum operator acting on the momentum eigenvector gives the momentum eigenvalue times the momentum eigenvector. Then the inner product p psi is nothing but the wave function in the momentum basis can be written as psi of p. Okay. Now this can be written as integral dqp. This is a momentum eigenvalue what we have written here at the middle. So this can be taken outside from that inner product. Then we'll have the inner product rp, then psi of p. Now what is rp? That we have seen in the last class. The inner product rp is nothing but 1 upon 2 pi h cross all raised to 3 by 2 e raised to I p dot r times h cross times psi of p. So again, the left hand side, the LHS is inner product r, the operator p times psi. Okay, so let this be equation number 2 and this be equation number 1. Now we can just calculate what would be minus IH cross dou by dou x acting on e raised to I px x by h cross. So that would be equal to minus IH cross. The derivative of any exponential would be the same exponential. So e raised to plus I px x by h cross. Then you had to we had to find the derivative of the power of exponential. So that would give I by h cross px. So I into minus I will become plus 1 and h cross would cancel. So that would be simply equal to px times e raised to I px x by h cross. Okay, so this is known to us. So then what would be the result of minus IH cross del acting on e raised to I p dot r by h cross? So this can be written as minus IH cross. Del can be written as x cap dou by dou x, y cap dou y plus z cap dou by dou z acting on e raised to I. P dot r is nothing but pxx plus pyy plus PZZ all divided by H cross. Okay. Now, if you do this carefully, then what will you get? Minus IH cross X cap. So what would be the result of dou by dou X? So that would give I Px by H cross plus Y cap I Py by H cross plus Z cap I Pz by H cross times this exponential would be common to all a raised to I Pxx plus Pyy plus Pzz all divided by H cross. Okay, now if you take this minus IH cross inside, then we'll get X cap Px plus Y cap Py plus Z cap Pz. Then this exponential e raised to I P dot R by H cross. Now this the quantity inside this bracket is nothing but the momentum vector. So it gives the momentum vector times a raised to I P dot R by H cross. So what was the left side? The left side is minus IH cross del acting on a raised to I P dot R by H cross. So this can be equation number 3. Okay, so equation number 3 is this, and this is my equation number 2. So there is a momentum times a raised to I P dot R by H cross. So that can be replaced with the LHS of equation number 3. So therefore, our inner product R momentum operator psi. This can be written as 1 by 2 pi H cross all raised to 3 by 2 can be taken outside. Then integral dqp minus IH cross del times e raised to I P dot R by H cross times psi of P. So what we have done is equation number 3 into. Okay, so this minus IH cross del, this del is the gradient with respect to the position coordinate. So since it is a partial derivative with respect to the position coordinate, we can treat all momentums are constant for that particular operation. So it is possible to keep this minus IH cross del outside the integration, because inside the integration only this quantity has the position coordinate. So there is no problem for taking this minus IH cross del outside the integral. So this become minus IH cross del 1 by 2 pi H cross all raised to 3 by 2 integral dqp e raised to I P dot R upon H cross psi of P. Now what is this quantity actually? This quantity is nothing but psi of R. So this can be written as minus IH cross del psi of R. So this is according to the Fourier transform. This is nothing but the Fourier transformation of psi of P. That would give psi of R, or it is minus IH cross del times the inner product R psi, or this can also be written as the inner product R minus IH cross del acts on psi. Now what is the left side? The left side was the inner product R P psi. So this shows that the momentum operator P is in general can be written as minus IH cross del. Now if we can find the components of the momentum operators, and the x component of momentum operator Px can be written as minus IH cross dou by dou x, and Py can be written as minus IH cross dou by dou y, and Pz is nothing but minus IH cross dou by dou z. So all these are the momentum operator in position basis. How to represent momentum operator in the momentum basis? Okay, so for that, that is very simple task. The momentum operator in momentum basis. So for that, we can take the inner product P, the momentum operator P times psi. Now that is simply equal to P, the momentum eigenvalue times psi. Okay, so this P is nothing but the eigenvalue. Okay, and so what would be the result? So that would be equal to P times the inner product P psi. So this would be equal to P psi of P. Okay, so then so the final thing is the inner product P psi. So what we are doing is we are finding the projection of the vector psi on the momentum basis, that is simply equal to the momentum vector times psi of P. So this shows that the momentum operator is equivalent to the momentum vector in momentum basis. Or this can also be written as the inner product P psi. So the momentum operator is nothing but the momentum vector in the momentum basis. So if you take the components, the momentum operator along x direction is simply px. The momentum operator along y direction can be simply represented as py, and the momentum operator along pz can be simply written as pz in the momentum basis. Okay, so there is no change for the momentum operator in momentum basis. So in the momentum basis, in terms of momentum basis vectors, the momentum operator is nothing but the momentum itself. Okay, so they are the representation of momentum operators. So the momentum operator Px, Py, Pz in position basis, in the momentum basis. So in position basis, it become minus IH cross dou by dou x. Momentum basis is simply Px, and Py in position basis it become minus IH cross dou by dou y. In momentum basis simply Py, and Pz in position basis it become minus IH cross dou by dou z, and in momentum basis simply Pz. So similarly, we can find the representation of position operators. So that I am leaving to you to do as an exercise. It was the same way you can we can find these representations. Position operators. So the position operators, we can find the x position operator, y position operator, and z position operator. In the position basis, this can be written as simply x, y can be written as y, and z can be simply written as z. And in the momentum basis, it takes a form plus IH cross dou by dou px plus IH cross dou by dou py plus IH cross dou by dou PZ. So the position operator in general, we can represent by symbol R, 3-dimension, and position basis become vector R. In the momentum basis, it takes a form IH cross the gradient P del P. And similarly, the momentum operator, 3-dimension, we can write as P. In position basis, it takes the form minus IH cross del. And in the momentum basis, it is simply the momentum vector. Okay, so this gives the complete the picture of the representations. Okay, so better we can use the same colors not to avoid the confusions. Okay. Okay, so these are the momentum basis and the position basis representations of the momentum operator and the position operator. So next, what we'll do is we'll try to calculate the commutator of the position momentum operators in some basis. Okay, whether you use a position basis or momentum basis, you will get the same result. So we'll try to compute those commutator relation in the next class. Okay, so thank you for watching this video. So I hope this is okay for you. So I am leaving one thing for you to do as an exercise. That is, you should find the position operator representation in position basis and momentum basis. You can follow the same steps that we have done for momentum operator. Okay, the main thing is, in order to start with the position operator in the momentum basis, we have to start with the inner product P R psi. That is the starting point. So from the starting point, we can show that is equal to the inner product P IH cross del P times psi. So this IH cross del P stands for the position operator in momentum basis, so that you can prove it in prove it yourself. And what is del P here? It is X dou by dou Px plus Y cap dou by dou Py plus Z cap dou by dou Pz. And symbol del is X cap dou by dou X plus Y cap dou by dou Y plus Z cap dou by dou Z. Okay, so once again, thanks for watching this video. So we'll see it with the discussion of the commutator relation of the position and momentum operator in the next class. Bye.